this lesson, you'll learn how to determine the number and types of roots for a polynomial equation and find the zeros of a polynomial function. How can the roots of an equation be used in pharmacology? When doctors prescribe medication, they give patients instructions as to how much to take and how often it should be taken. The amount of medication in your body varies with time. Suppose the equation m of t equals 0.5 t to the fourth plus 3.5 t cubed minus 100 t squared plus 350 t models the number of milligrams of a certain medication in the bloodstream t hours after it has been taken. The doctor can use the roots of this equation to determine how often the patient should take the medication to maintain a certain concentration in the body. You have already learned that a zero of function f of x is any value c such that f of c equals 0. When the function is graphed, the real zeros of the function are the x-intercepts of the graph. Let f of x equal, the given, be a polynomial function, then c is a zero of the polynomial function f of x minus c is a factor of the polynomial function f of x, and c is a root or solution of the polynomial equation f of x equals 0. In addition, if c is a real number, then c0 is an intercept of the graph of f of x. When you solve a polynomial equation with degree greater than 0, it may have one or more real roots, or no real roots. The roots are imaginary numbers. Since real numbers and imaginary numbers both belong to the set of complex numbers, all polynomial equations with degree greater than 0 will have at least one root in the set of complex numbers. This is the fundamental theorem of algebra. Every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. Now, to start us off slowly here, solve, state the number and type of roots. Well, to undo minus 10, we're going to add 10 to both sides of the equation. So I solved it. I have a equals 10, so I get exactly one real root, and it is at 10. Solve, state the number and type of roots. Okay, I need to factor. I want factors of negative 48 to give me a sum of 2. So I could do x plus 8 and x minus 6. So my two roots are negative 8 and positive 6. So it just got twice as challenging. We went from 1 to 2 real roots. And this time I can see I have a greatest common factor of 3a right off the bat. And when I factor, I have a squared plus 6 left. And I can't factor that anymore. So my two factors are, I'm going to have 3a equals 0. And a squared plus 6 equals 0. If I divide both sides by 3, I have 0. That's lovely. I'm going to have to subtract 6 and take the square root of both sides. And square root of 6 and square root of negative 1 is I. So it looks like this time we ended up with one real root at a equals 0 and two imaginary roots at positive and negative square root of 6i. This time I can see I have difference of squares because y to the fourth is a perfect square. Square root of y to the fourth is y squared. Oops, square root of 16 is 4, not 16. And y squared minus 4. Now, the first guy can't be factored anymore because, well, it's a sum. But this is a difference of squares, so I could factor that again to y plus 2, y minus 2. And that's all I can do with factoring. So I've got three factors. I can make three little mini equations. If I subtract 4 from both sides, I've got y squared equals negative 4, so y is going to equal plus or minus square root of 4 is 2, square root of negative 1 is I. Subtract 2 from both sides, and y equals negative 2. Add 2 to both sides, and y equals 2. So this equation had two imaginary roots at 2i and negative 2i, and two real roots at negative and positive 2. There seems to be a pattern. My degree was 1, I have 1 root. My degree is 2, I have 2. My degree is 3, I have 3 roots. My degree is 4, and now I have a total of 4 roots. The corollary to the fundamental theorem of algebra, a corollary is something easily proved from a theorem, is a polynomial equation of the form p of x equals 0 of degree n with complex coefficients has exactly n roots in the set of complex numbers. Similarly, a polynomial function of the nth degree has exactly n zeros. René Descartes was a French mathematician and philosopher. One of his best-known quotations comes from his discourse on method, "I think, therefore I am." French mathematician René Descartes made more discoveries about zeros of polynomial functions. His rule of signs is given below. If p of x is a polynomial with real coefficients whose terms are arranged in descending powers of the variable, the number of positive real zeros, y equals p of x, is the same as the number of changes in sign of the coefficients of the terms, or is less than this by an even number, and the number of negative real zeros of y equals p of x is the same as the number of changes in sign of the coefficients of the terms of p of negative x, or is less than this number by an even number. Now, when I took this course in high school, we did not have the aid of technology you do today, and this was amazing. It's still handy to know, but not as cool as it was then, frankly. Okay, they ask us to state the number of positive real zeros, negative real zeros, and imaginary zeros. Okay, we already have the positive set up. This is p of x. We should have a possible of 6 total, because this is a 6th degree. Okay, I have 1 sign change, 2 sign changes. Okay, I have 2. Okay, so I could have 2 positive zeros or less than that by a multiple of 2, so 2 or 0. Okay, next we need to evaluate p of negative x. So every place there was an x, I replaced it with negative x. So if I'm raising a negative to an even power, it's going to stay positive, or change back to positive. So this is just going to stay the sign it was. Now, if I'm raising a negative to an odd power, negative 1 times negative 1 is 1 times negative 1 is negative 1. So this is going to change to minus 4x cubed. Even power stays the same sign because negative times negative is positive. And odd changes, negative times negative is positive. And the constant really doesn't change. So now we're looking for sign changes, and I've got negative, negative, oh, positive, oh, negative. So since I have 2 sign changes, I can have 2 negative zeros or less than it by an even number. Now we don't have a handy-dandy sign rule for the imaginary numbers because there's no way to make p of I or whatever. So they made a chart. If I have the highest number of positive and the highest number of negative, 2 and 2 leaves 2 imaginary to get a total of 6. But wait, I could have only 0 positive, 2 negative, that makes 4 imaginary to get a total of 6. Or 2 positive, no negative, 4 imaginary and 6. Or none, none, and all 6 are in the realm of imaginary. So to write down a final answer here, our positive zeros, we could have 2 or 0. Negative, we could have 2 or 0, and imaginary could be 2, 4, or 6 zeros. Recall that the number 0 has no sign. Therefore, if 0 is a 0 of the function, the sum of the number of positive real zeros, negative real zeros, and imaginary zeros is reduced by how many times 0 is a 0 of the function. Okay, this is the real deal. Find all the zeros. Okay, first I'm going to check to see how many sign changes I've got to look for how many positive zeros, how many negatives to look for. I've got 1, 2 sign changes. And to find the negatives, we can have 2 or 0 positives. For the negatives, I'm going to have negative x cubed minus x squared minus 2x plus 4. So looking for sign changes, I've got 1. Yes, we at this point in high school did lots and lots in synthetic division. We were glad to know we could only have a possible number of 2 positive and maximum of, and it had to have 1 negative on this one. You guys have a calculator, so type it in your table feature. And with very little scrolling, I found that I had a 0 at -1. That's good. I was supposed to get 1 -0. Scrolling up, I got really big numbers. And don't you know, scrolling down wasn't a whole lot better. So I am pretty confident that the only real 0 I'm going to get is at -1. Now the directions didn't just say find the real zeros, they said find all. But no worries, we know that -1 is going to work. So we're going to multiply and add, multiply and add, multiply and add. We can reconstitute it to look like a polynomial, but maybe you don't even want to because there's a, b, and c that we need for quadratic formula. So plugging in, we've got -b, so -2 is 2, plus or minus the square root of b squared, so -2 squared, minus 4ac all over 2a. So my discriminant, I've got 4 minus 16, that'd be -12. And we've simplified square root of 12 enough times. I feel confident we're good with the 2 square root of 3. Square root of -1 is I. And wouldn't you know, they're all divisible by 2. So if we divide everything by 2, we get 1 plus or minus square root of 3i. And the graph confirms we had 1 real 0 at -1, and that's all it's going to cross, so the rest are imaginary. The graph doesn't help us check the imaginary roots as to accuracy, but we know there are 2 of them. Can you kind of see why there's always going to be 2 of the complex roots, this plus or minus? In Chapter 6, you learn that solutions of a quadratic equation that contains imaginary numbers come in pairs. This applies to the zeros of polynomial functions as well. For any polynomial function, if an imaginary number is a 0 of that function, its conjugate is also a 0. This is called the complex conjugates theorem. Suppose a and b are real numbers with b not equal to 0. If a plus bi is a 0 of the polynomial function with real coefficients, then a minus bi is also a 0 of the function. Write a polynomial function of least degree with integer coefficients whose zeros include 4 and 4 minus I. Well, I know that complex conjugates come with friends. So if 4 minus I is a factor, so is 4 plus I. And we know we have a 0 at 4. And if we know what the zeros are, all we have to do is put an x minus each of the zeros, and voila, we have something to multiply out. Okay, it's probably going to be a good idea if we distribute those negatives. So the opposite of negative, positive 4 is -4, opposite of minus is plus, and so on. And we're distributing, so we've got x squared minus 4x minus ix, and minus 4x plus 16 plus 4i. And finally, ix minus 4i minus I squared. And now the fun begins, because our opposites get to cancel and our opposites get to cancel, and well, I squared is the same as -1, and so instead of minus I squared, I could put plus 1. So when we combine our likes, -4 plus -4 is -8, and 16 plus 1 is 17. Now we get to distribute that out. So we've got x cubed minus 4x squared minus 8x squared plus 32x plus 17x minus 68. And we combine our like terms, which I stacked on top of each other. It fits better on the paper anyway, and it's just handy. And I have x cubed minus 12x squared plus 49x minus 68. The fundamental theorem of algebra: every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. Use Descartes' rule of signs to determine the types of zeros and polynomial functions. Complex conjugates theorem, if a plus bi is a zero of a polynomial function, then a minus bi is also a zero of the function.